Hello everyone and welcome to another video on Python programming. In this video we are going to be learning about the topic of decorators. To start off with, let's first understand some basic concepts. Now in Python we know that functions are first class objects, and that means that functions are objects and they can be referenced to, and they can be passed to a variable, and they can be returned from other functions as well. Functions can also be defined in another function and can be passed as an argument to other functions. So decorators allow programmers to modify the behavior of a function or class. Decorators allow us to wrap another function in order to extend the behavior of the wrapped function without permanently modifying it. Now, any generic functionality that you can tack on to an existing class or function's behavior makes a great use case for decoration. Some of these include rate limiting, caching, logging, enforcing access control and authentication, instrumentation, and timing functions. Now you have to remember that function names are references to functions and that we can assign multiple names to the same function. So for example, if you see here, I have defined a function called success, which does basically you pass an integer and it returns 1 plus that integer. So if I do success 10, it should give me 11, as you can see here. Now if I'm gonna say successor is equal to success, I've basically created another function called successor which does the same job as the success function. So now if I pass 20 to successor, it should return 21, as you can see here. So as you can see that we have two names, success and successor, for the same function. An important fact is that we can delete either any of the functions, and you won't delete the other one. So if I said delete success, and if I tried to pass 10 to the other function called successor, it would still execute the whatever task the function is supposed to do. Now let's look at an example of a function inside a function. So I've defined a function called f, in which I have defined another function called g, which has two print statements that you can see here. The function f itself has two print statements, and at the end of the execution of function f, we call this function g. So let's see what happens when we actually execute f. So let's look at it on this side. So if you see here, this is where I've defined it. Now let's call my function f and let's see what happens. As you can see, first when you execute function f, it will create this function, and then it will print these functions, and then it will do a call to this. And when we call this function g, it's going to do two of its own print statements, as you can see in this order over here. So this is an example of a function within another function. Let's look at another example of something similar. If you see here, I've defined a function called temperature where I can pass some value for T, and I have defined another function within this called Celsius to Fahrenheit, and basically I'm doing the conversion. So when I execute this, what it should return me is I'll pass some temperature, and it will return me the temperature in degrees. So for example, in this case, I have passed temperature 20. So let's see what does it pass, what result does it give to me in degrees. As you can see, it says it's 68 degrees. Now let's look at another example of a function within a function, for a very common example for the factorial function. So if you see here, I've defined factorial n, and I'm saying if the value that is passed in n is equal to 0, return me 1. Otherwise, return me the product of that number times, and I'm going to do a recursive call back to the same function, except now I'm not going to pass n but n minus 1. So what this should do is, if I pass 10 for example, it will basically check, okay, since 10 is not equal to 0, it will go here, and it will return me 10 times factorial of 9, and that will do 10 times 9 times 8, and then so on until we reach n is equal to 0, where it will just say, okay, return 1. So what you will effectively get is 10 times 9 times 8 times 7, so on until 1, which is basically factorial of whatever we have passed. So let's execute this. See, I'm going to check what is the factorial of 5 here, and as you can see, it gives me 120. Now let's include a line, let's raise an exception by an else statement, which will basically raise a type error, and it will tell me that if I pass a number n which is not an int, and if it's not greater than or equal to 0, it should give me this error message. So I have included this extra statement in this just to check. So if I pass 9, as you can see, it should give me a valid result, which is 362880. Now what if I pass -5? So let's execute this. As you can see, I get the type error that I have raised over here in case I meet such a condition. And in this case, you cannot find the factorial of a negative integer. So that is why my type error gets raised over here. If you actually look closely at this program, you will notice that each time I call back my function factorial, so if I gave it 5 initially, it will check for the this condition, and since it will meet the condition, we can continue. But the next time when we call factorial for 4 and then for 3 and 2, each time is going to do this check. That's kind of redundant because we know that if we passed 5 in the beginning, until we decrement it to 0, we are going to only get the valid numbers 5, 4, 3, 2 and 1. So we don't need to do this check at every point. We just need to do one check. So a workaround for this would be in this code that I've written over here. And in this, I've basically defined a factorial function called n, where I'll pass my integer initially. And within that, I've defined the actual function where the actual results will be calculated, and that's called inner factorial. This is where this is basically the actual factorial calculating part. And if you see this if statement block, this is my check. So this will basically be the only check that will happen. So out here, it will check whether the n I have passed is a valid integer and equal to or greater than 0. And if it is, then we will perform this inner factorial function, where we won't be doing any more such checks. We will only calculate the factorial. And if it's not, then we will raise this exception just once, and we will exit the program in case we've given a wrong number. So let's look at an example for 3. So as you can see, at each step of my calculations, I'm going to return whatever value I have at that point. So basically, if I give 3, you will notice that you will get 0, 1, 2, and 6 if you multiply it in the right way. So let's do this. As you can see, factorial 3. One second. So I have to execute this. Now if I execute this, you can see I first get, because initially it will check, when I move into inner factorial, it will check if n is equal to 0. It will basically return whatever value I have at that point. So basically this is the order of calculations in a backward way. So you can see here it will first be 1, and then 1 times 2, and then 2 times 3, which is 6, which is what we get. So don't worry about the order in which we are returning these values. This is basically just a reverse way in which the program will fetch our values. So yeah, this was basically how we reduce the redundancy in the check part of our function. Now let's look at some examples where a function will be returning another function. So as we know, the output of a function is also a reference to an object, and therefore functions can return references to function objects. So out here, if you see, I've defined a function called f, which will take a parameter called x, and then within it I've defined a function called g, which will have a parameter called y. And this g will basically return y plus x plus 3, and the function f itself will return the function g. So if I pass 10 in function, so what this will do is it will create a function called g. I will create an instance of a function called g, and that object is going to be returned to us because we basically return g when we call function x, right? So if I execute this, you will see that when I say f10, it will give me some object location of a function called g. Now if I want to see the result of what I get for this function g, I have to pass something within g itself. So out here, what I'm going to do is I'm going to store this function object in a variable called nf1. Once I've done that, I can pass another parameter for this nf1 object. And since we know this nf1 is a variable name for the function g, so when I pass nf120, I'm basically passing this y parameter. So since now I have passed 10 for x and I have passed 20 for y, oops, one second, yeah. So what I will get returned is 20 plus 10 plus 3, which is 33. When I do nf1 and I pass 20 as the parameter here, as you can see, I get 33 over here. Now let's look at a function where we will implement polynomials of degree 2, and then we will actually extend that to polynomials of any degree. So I have created a function called Polynomial Creator, where I pass 3 arguments which will represent the coefficients. So a will represent the x square coefficient, b will represent the x coefficient, and c the constant. So I have defined within this, I've defined a polynomial function called x, where I will pass my value for the variable x, and I want to get returned the value for this polynomial. So as you can see here, initially the first function will return this object, and then for this object itself, I will have to pass another argument, where I'll pass the value of x. So let's create, so I'm going to create two instances of this polynomial function. In the first instance, my coefficients are, as you can see, 2, 3, and -1. In the second case, it'll be -1, 2, and 1. So once I execute this, oops, let me execute the function initially. Yeah, there you go. So if I execute p1, it will basically give me a object location of the polynomial function for p1, which is represented by this basically. So now what I'm going to do is I'm going to iterate through values between -2 and 2, not including 2, at steps of 1. So I'm going to iterate for -2, -1, 0, and 1. And I'm going to say, initially print me the values of x that I'm going to pass in this column, this first column. And then I'm going to say, okay, what are the results for the first polynomial object where the coefficients are 2, 3, and -1. And then in this column, give me the values of the polynomial with these coefficients, -1, 2, and 1. So when I execute this, as you can see, these are my results. Now, what if I wanted to do the same thing for arbitrary coefficients, as in a polynomial of nth degree? You know, I'm not specifying the exact degree. So this I can do with this slightly more complicated program, which is actually very simple. So if you see this function, I've defined a polynomial creator function again, but in this case, I have passed variable number of arguments. So this asterisk basically means I can have any number of arguments here, and this will be an iterable with any n number of objects that can be iterated upon. So, and that will be called coefficients. So within that, again, I've defined polynomial x. Now what I've done is I've initialized some variable called res, which will basically be my result variable. And what I'm going to do is I'm going to for loop through this coefficients iterable. And what this basically does is, in a backward way, this is basically going to iterate through the array or the list or whatever we have of coefficients in a backward way. So if I pass 6, 7, 8, 9, it's going to give me 9, 8, 7, 6 in that order. And what this enumerate function will do is it will assign an index to each of the values and coefficients. So for example, I can just show you over here what this means. So if I created a array called say coefficients with some random values over here, right? Now if I'm going to perform this line, right? Now let's see what happens when we do a for loop. Let's see what values we get for index and when we do this, execute this line. So if you see here, now once I execute this, as you can see, what I have done is coefficients. Oh, I made a spelling mistake. This is taking from a different variable. So let's fix this. So as you can see, I've entered 4 objects, 4 integers, 1, 23, 4, and 45. And when I do this for loop, I basically want to assign some index value 0, 1, 2, and 3 to each value in this list, but in a backwards manner. So this will be the 0th item, this will be the first, this will be the second, this will be the third. So that's what we are doing in this function as well out here. We're basically going to use this enumerate function to, now if you see this result is basically going to add each component of this polynomial. So if you see closely, what this is going to do is it's going to first, in the first step, is going to find out, well, what is the value of this, the constant term. And then in the next step, is going to find out what is the value of this. And it's going to keep summing it up. It's going to sum this part up until the end. And then we will get our final result in this variable res, and we're going to return that over here. So if you see here, I've done the same thing. I've created 4 function objects, and they're called P1, P2, P3, P4. And now I'm going to iterate through again -2, -1, 0, and 1 as my different x values, and I'm going to see what are the different values for each of these polynomials. So if you see here, my first polynomial is basically, it has only one coefficient, so it's a polynomial of the 0th degree. So basically whatever I pass for x, that itself should be my result. So actually this is a polynomial of 0th degree, so this is basically the only result we will get. So the constant is 4, we will get 4 in every result. So if you see here, what I'm printing is the x values first, and what are their respective polynomial values for each of these objects that we've created. So this is a constant, so P1 will only have the result 4. This is P2, so this is a polynomial of degree 1. So it's like saying 2x plus 4, and where x takes values -2, -1, 0, and 1. And in this case, you can see this is a polynomial of 4th degree. So it's like saying x to the power 4 plus 8x cubed minus x squared plus 3x plus 2. So when we replace x with minus 2, minus 1, 0 and 1, we get the respective values in the P3 column over here. And for P4, it's basically a square polynomial. So yeah, this is an example of how we can create we can do a polynomial creator and get our results accordingly. Now, interestingly enough, what we've done here is basically, like, for example, let's look at P3, right? P3 is basically this polynomial. Now, this polynomial function inside our decorator, polynomial creator. So all these examples that I've been showing you where functions are within functions, if you think of it, it's like I'm giving some basic function extra, like I'm doing something extra within them, right? So we can use decorators for this. And in our example over here, what I can do with this function is I can implement the same operation more efficiently by using a decorator within our main function. So we can factorize it in a way that it does not need any exponentiation. So we can, if you think of it, this polynomial can be represented like this, right? If you think of it, it's basically this times x plus some constant, and then that whole thing is again times x plus some constant. Since this is to the power 4, this is all we need. But if you think of it, if we keep going further, all you have to do is again enclose it in another bracket and then do times x. So we can basically use a decorator to do this function. So if you look at this function over here, what I've done is I've created the same polynomial creator with variable number of arguments. But inside this function, like what I've done in the form of a decorator is that I'm going to implement this polynomial by calculating the result in this manner, where it's going to be very much more efficient, and you don't have to keep exponentiating like how I did in this example. So that's what I'm doing over here. And if you see, that is basically implemented over here through this. So when I do the same, when I execute the same thing, and if I go through the for loop again, it should give me the same results, but it's much more efficient. Now let's look at another example of a simple decorator. So I've defined a function called our decorator func. Now this will basically be, this is a reference to another function itself, if you see within this. But inside my decorator, I have a function wrapper where I'm going to print this statement before actually calling the function x, before calling the function. And I'm going to perform a print statement again after that. And I'm going to return the function wrapper at the end of executing the decorator. So let's look at what happens when we define this function foo x. So this is basically a simple print statement where I'm saying hi, foo has been called with whatever this is, argument. So now let's execute what happens when I say foo hi. So as you can see, let's execute the whole thing. So yeah, as you can see here, I have executed this. It says this is the print statement that I've basically written over here, and this is what gets printed when I call this function here. Now when I move on to the next statement, what I'm declaring is I'm going to now decorate foo with f. Now what this means is I've now created this this decorator object basically. So let's look at what happens when I execute this, and then I'll try to explain to you. So when I execute the whole thing, you can see something else is happening now. So we call foo after decoration, then we have this before calling foo, and this is basically this print function. This is the print function that gets executed here. Now we have this is the function call. This is basically the function call, which is basically this foo function, and this line is being printed from this. So if you see here, I'm getting some results from this, like from this decorator itself, but I'm also calling upon the function that is being referred to by this decorator. So I'm doing two things. I'm doing the main thing, which is being executed here, which is the result is here, but I'm also decorating it with these two lines, which comes from this decorator called our decorator. So let's look at the explanation. So if you look at the output of this previous program, we can see what's going on, and that is that the decoration foo, this when we did this line, which was over here, it's a reference to the function wrapper, which is this. Now in this function wrapper, this function itself, right, like this function that we defined here, that will be called as well, but we will also have a bunch of extra print statements in the form of these two lines, which you can see over here, before calling and after calling, that we've also done along with this. So this is a simple example of how we've used a decorator to modify our basic function. Now this usual syntax for decorators in Python is with the at symbol. So we can write the same thing like what we did before through this. So we write at our decorator, and this will basically apply the decorator to this function foox. So when we do at our decorator and then we define this function and we call it, it will basically do the same thing as doing this, for example. So if I execute this, you can see the same thing has happened here. Now I'm going to give you another example of a decorator. Remember the factorial function that we did earlier, where we did a check within the factorial function. Well, let's see how we can use decorators to aid our case in this. So as we know, before we calculate the factorial of something, we want to make sure that whatever we pass is greater than or equal to 0 and it's an integer, right? So let's define a decorator which will basically do this. So in this decorator, what we're going to do is we're going to create a function called helper, where we're going to perform this check, and this is going to be our decorator basically, right? However, so what this will do is basically this decorator will say, okay, if this check is met, then you can return the value of function of x, which is the function is what we pass in this as an argument to the decorator. So once the check is done, we can perform a factorial. So that's what we're going to do here. So we've defined our decorator. Now we're going to use the decorator here, and we're going to define within it a factorial function. So when we actually perform the factorial, like for some numbers, like we're going to do factorial of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all these 10 digits from 1 to 9, sorry. So if you're going to do that, what it's going to do is at each step, so for the value 1, it's going to first check whether our integer passed is actually the correct form of an integer, whether it's in integer and greater than or equal to 0. So once that is done, then it will move on to the actual factorial function. So when we do for I in range 1 and 10, since every number is valid, we won't get nothing wrong will happen. There won't be any exception raised. But what if we did factorial -1 now? Now the factorial function itself doesn't have a check, but since we have a decorator around this factorial function, it's first going to do this check, and if it finds an error, it will raise an exception. So if I do this, if you see, when I execute, it raises my exception. So this is how we have added some functionality to the original factorial function using this decorator. As always, thank you for watching this video. Do like, share and subscribe, and I hope to see you in the next video.